Okay, going to start with chapter 12, kinematics of a particle, okay, 12.1 and 12.2. Kinematics of a particle, basically it's this idea that we're looking at and analyzing the motion of a particle or a dot or a point without being concerned with the forces involved that cause the motion, okay? When we get into kinetics, that's when we're actually looking at the forces that cause the motion. So some applications, we're looking at the motion of large objects and rockets, airplanes, cars, and considering it as if that object was a particle, meaning like the center of mass of that particular object. Okay. Uh, and what we're going to do is actually go and you know develop an equation to represent that. And really, what we're trying to do is we're representing its position in terms of its like initial position where it started, any kind of velocity or initial velocity, and its final or its acceleration. So those things together can give us the position or represent the position at some point in time. We'll also look at like straight line motion. Um, in this case, here's an example where you have some quantities that will represent the motion. We're going to have some position s, like where it's located, and it's going to be a function of essentially wherever it started from and its acceleration and velocity um, during that time from when it moved from, let's say, the origin to its position. Okay. So briefly, where dynamics falls in, it's actually one of the areas of study of mechanics, and the other one is statics. And the real difference between these, of course, is that statics is where all the forces or the sum of all the force vectors will add up to zero. So you'll have an equilibrium condition, which essentially means there's no acceleration. Okay. It could be stationary or it could be in motion as long as there's no acceleration. And dynamics is now, and we have two sort of main categories under that, or two main areas under that, and kinematics and kinetics. And the first one we're going to look at is kinematics, okay? Okay, so we have to define some symbols that we'll use. We need to look at, position, we need to look at velocity, and we need to look at acceleration, okay? Now we can represent, in straight line motion, we can just use the symbol S to represent a position, okay? If we're talking about, so it's not necessarily in a straight line motion, or we can't represent it as a straight line motion, we have to be concerned with like the direction also. Okay, so we have this thing called R, which is essentially a position vector, meaning that it has a magnitude and direction associated with it. Okay, so if we just look down here, if we're talking about change in position, right? We could use delta R, or delta R be used by this author, and essentially what it's saying is like where were you originally? Went through some change in position, so it's like original minus the final position here, or the position at the second point. In this case, P prime is just going to be the difference between the two. Okay. Now, if we're talking about purely straight line motion, you can just represent it as a scalar. So the next quantity we're going to look at is velocity. Okay. And velocity essentially is just, um, and you could look at it in terms of average velocity or instantaneous velocity, which we'll look at here. And the average velocity basically says between, you start at point P, you move to point P prime here, and what's going to happen is you have some essentially change or some distance that's traveled and over some period of time. So in this case, if we wanted to find the average, we would just use that vector, the delta R vector over delta T, okay? Or if we had the instantaneous form, and this is like the general form for the average. Of course, if it was straight line motion, this would just be delta S, right? The next one is if we're talking about the instantaneous, or if we're looking at like instantaneous velocity, let's say we're looking at it at any point, it becomes the derivative, right? It's just delta r over delta t, right? And like I said, speed is just the magnitude of the velocity, so ds over dt. So if this is just, you're looking for speed, not necessarily in a specific direction, and this works well for straight line motion, it's going to be just delta s over delta t, okay, or ds dt. And then you can also come up with an average speed there, which is just, the total distance from, either from one point to another divided by delta t. And the last quantity that we're going to look at is the acceleration, okay? And we have acceleration, of course, is the change in velocity with respect to time, right? So the instantaneous form, it's just going to be dv over dt, which is our vector form of this, okay? So we also have to be concerned with the direction. Or if it's straight line motion, of course, we can always do just a equals dv over dt, or the second derivative of the position, okay? First one would give you the velocity, the second one gives you the acceleration. All right. Now to solve for velocity. So this is like going in the other direction, where you're given acceleration and use the integral or integrate between the limits to determine the unknown. And in any case, like here, if the velocity is given as a function of time, in this case, any of these are unknown, t, v, or v naught, any of those you could solve for those specifically at, you could find velocity at a point in time, or, if you knew velocity at some point, then you could solve for t. Essentially, any of these are unknown, you could find them, any one of these. Now, if your velocity is given as a function of position, this is the form you would use, okay? So in this case, there's no time defined, or velocity isn't a function of time, so time is not your independent variable. And then also position. So if you're solving position, this is the form you would use, right? So it's basically just going in a direction. So this one's like if you're given velocity, you would perform the integral to find out what your position is, okay, at some point in time, right? So the one note here, of course, is this S naught, V naught. These are the initial position and velocity at t equals 0. Now we can go ahead and simplify this somewhat. If we have constant acceleration, we can perform the integration here. Of course, when we do that, this just simplifies. The right side just is AC t on the right-hand side, and the left-hand side becomes, v minus v naught. And then if we just move v naught over to the other side, we have this equation. And we can do the same thing here to represent position. And in the last case here, you can actually do, perform what we have in the other form, where we have, we don't have t as our independent variable, we now have s. You can solve for, if in this case the velocity is given you as a function of position, you can actually come up with a new form of this. What's the difference essentially from like this form and this form? This one is that if you are not given, position information, I'm not given time information, but you're given position information, you can solve for velocity. Okay, but these three equations are essentially what they are. They're the when the acceleration is constant, these integrals essentially simplify into this forms. Okay. Okay, so here's an example, and in this case, a particle travels along a straight line, and so we don't have to worry about it on a vector. We can just use, the scalar forms for position, velocity, and acceleration. And so we're given a velocity, and we can see velocity is a function of time. And we're given some other information. We're saying our position is equal to 0 when t is equal to 0. All right. Now, of course, in this case, we can see that, when we go ahead and perform the derivative, of course, this is not a constant acceleration, right? All right, but we'll just follow the general approach. So we're looking for at some time t, in this case 4 seconds, we're going to look for the position and acceleration of the particle, right? Well, we're giving it as a function, we're giving velocity as a function of time. So this is, of course, to find the acceleration, we use the equation we had looked at previously, which is just acceleration is equal to dv dt. Okay, so that's how you can solve for velocity. Just taking this derivative with respect to time. And then we can perform the integration to determine the velocity as a function of, to calculate its position, right? All right. Okay. So, once you come up with a proper approach, then it's just a matter of performing the math associated with it. And so here, just perform a derivative on this, and when you do that, dv dt just becomes 4, and then 6t. Okay. What do? Substitute in for t equal to 4 seconds, and you can come up with the acceleration at that point in time. Right? Since it's negative, really, it's just telling you that it's deceleration, right? So by the direction, it's defining off to the left, where we would define positive acceleration off to the right, or motion is off to the right. Okay. The next part is just, of course, you can rewrite the velocity in terms of the ds dt, and then rearrange it. When you do that, what do you have? You're going to perform the integral on the right-hand side. And this one, of course, is just going to evaluate s minus s naught. The left-hand side is just s minus s naught when you perform the integration. And on the right side, it's going to be 2t squared minus t cubed. And then, in this case, you can solve for position, right? So this is telling you, it's off to the left because it's negative. So your position's actually to the left of the origin in the end. So just do 4 squared, substituting for t, and then 4 cubed. Okay. Okay, for the next problem, we're looking at, we have a sandbag dropped from a balloon, and it's ascending at a constant speed of 6 meters per second. The bag is released with the same upward velocity of 6 meters per second at t equals 0 seconds, and hits the ground when t equals 8 seconds. So we're looking for, in this case, we're looking for the speed of the bag as it hits the ground, and the altitude of the balloon at this instant. Okay. So what we can recognize here is that there's a constant acceleration, right? For, in this case, for the acceleration down toward the Earth, right? Gravitational acceleration. So since it is constant acceleration, we can use one of our standard forms for the equation. And we can just go back a little bit here, do a few slides back. Oh, too far. Come forward. And one more. Here we are. Okay. So since acceleration is constant, we can actually use this form, right, of it. All right. So we can see from here that we're going to be looking for position, right? So we can actually find out what the height is at the point where, how high was it when the bag was released? How high was the balloon when the bag was released? Okay. So what we do is we say, in this case, we can define any direction we want, right? So we define positive direction being down, okay? And when we do that, what that does, you'll recognize over here, of course, is that now acceleration is in the same direction of our motion, okay? So it's positive. So all we have to do is substitute in. What we say is that the initial position is actually just, the initial position is essentially, we define that as 0, right? So wherever it started from, we're defining when it was released. That's like our point, the 0 point, and going down toward the Earth is our positive direction. So we define that as our origin, let's say. And then the velocity, so we know that initially the bag was going upward, which essentially is in the opposite direction of our motion. So we have a negative 6 meters per second, and then times time. Okay, time would be our t, which is the 8 seconds. And then the second part of it is just 1/2. Here's our gravitational acceleration. Notice the positive because it's going down. Same direction of our motion. And then t is 8, so you just square that. So we've now determined how high was the sandbag when it was released from the balloon. Okay. So now what we can do is one of the things is it was defined in the problem is that the balloon is rising at a constant rate, right? So there's no acceleration. So the distance that the balloon has traveled, so we could just change the direction here. We can say it's going positive up, right? It really matters how we define it at the end, right? Because what we're going to end up doing is we're going to have like this distance and this distance put together. Since there's no acceleration, our equation just simplifies to, the velocity of the balloon, which is constant, times t, okay? And that comes up to be 48 meters. So we add those together, and then we determine that the total altitude, of course, was 314 meters, right? So how high was it before we released the bag, and the distance, the distance that it traveled upward while the bag was falling to the earth, okay? And then it comes up 314. And the second part of this is what's the velocity of the bag when it hits the ground. Okay, initially it was going, and in this case we're defining it saying it's positive going down. That's what we originally had defined for the positive direction of motion is going down of the sandbag. And that just comes up to be, well, we had some initial velocity which was going in the opposite direction, right? So that was going up, so we define that as negative. And then the constant acceleration times the time. And that will give us our final velocity of that bag, okay? So as it was going down, of course, it's speeding up, and this is the rate which is speeding up, essentially.